Chapter 12, Part 5, Keto-enol tautomerism. Aldehydes and ketones exist in two different forms. We have the keto form, which contains the carbonyl that we are used to seeing, and we have the enol form, which contains an alkene and an alcohol attached to the same carbon. These two structures are at equilibrium with each other. They are not resonance forms. We show this by using an equilibrium arrow between the two of them. Now, another way that we can tell that these are not resonance forms is that bonds have been made and broken in order to get between the keto form and the enol form. So notice in the keto form, we have our carbon-oxygen double bond, which makes our carbonyl. And this carbon here, which is the alpha carbon, we call it alpha because it is directly attached to the carbonyl, is a CH3 group in this molecule. Looking at the enol form, we can see very clearly that we no longer have a carbonyl, so we can tell that has changed. But looking at what used to be our alpha carbon, we can see that this is now a CH2 group. So the hydrogen that used to live here is now more or less up here. That's not exactly how it happens mechanistically. We're going to look at the mechanism on the next slide. But if you're just comparing these two isomers of each other, you can see that that's where the difference is. So bonds have been made and broken in order to get from the keto form to the enol form and vice versa. So let's take a look at the mechanism of how these bonds are made and broken. So starting with the keto form, if we are in acidic conditions, which we would be for going between the keto and enol forms, we are going to start by protonating something. Anytime you're in acid, I always tell you to protonate something. And when we talked about carbonyls initially, we pointed out that the carbonyl carbon is partially positive, the carbonyl oxygen is partially negative. So acids are going to end up on the oxygen. So the oxygen picks up the proton, and we end up with our new structure, which has a proton on the oxygen and a positive charge. Now, this structure has a resonance form, which allows us to show the double bond breaking and putting its electrons on the oxygen. So I'm going to use the double-headed arrow to indicate that this is resonance and not equilibrium. And this gives us the alcohol group that we need for our enol and puts a positive charge on what used to be the carbonyl carbon. So this is a resonance form that we've seen before when we first looked at carbonyls, or at least something similar to it. Now from here, we need to create a double bond between the alpha carbon and what used to be the carbonyl carbon. So this is where our water molecule comes in. We are going to deprotonate at the alpha carbon. And we're going to use water to do it. So water is going to pull off this proton, this bond is going to break and form our double bond. So that we end up with our alcohol and our alkene touching the same carbon, our enol form. We also end up making an equivalent of hydronium, which is okay because those were our conditions initially. Now, to go the opposite direction from enol to keto form, we just have to do everything we just did, but in reverse. That's kind of the beauty of equilibrium, is that if the reaction goes forward, then it also goes backward. And those steps are always going to be just the exact opposites of each other. So for example, we ended our previous mechanism by deprotonating at the alpha carbon. So to start our next mechanism, we're going to start by protonating at the alpha carbon. Now, we're protonating at the alpha carbon because that's what we need to do, but also that does follow our Markovnikov addition rules that we've previously seen for alkenes reacting with acids. So we put the proton, oops, switched to yellow somehow. We put the proton on the least substituted carbon, which is the alpha carbon, and that gives us the more substituted carbocation. And then we have a resonance form where we can reform our carbonyl carbon, or sorry, our carbonyl double bond. Which gives us an intermediate that we saw up above as well. Now to get to this from our starting material, we protonated our carbonyl. Now we're going to deprotonate. And deprotonation was also the last step of our previous mechanism. It's just we previously deprotonated at the alpha carbon. Got ahead of myself there. Started writing hydronium. So I'm going to break this bond and give those electrons back to the oxygen. And this gives us the keto form plus hydronium. So these mechanisms are exact opposites of each other. So you may be wondering why we're talking about tautomerization. Now, tautomerization is important because it leads to a process called racemization, or the formation of a racemic mixture. Now, we've previously seen racemic mixtures when we were working in our stereochemistry chapter. We've also seen racemic mixtures when we looked at the products of SN1 reactions. Racemic mixtures mean that you have a 50-50 blend of two enantiomers, or possibly two diastereomers. Now, how that happens when you have a chiral alpha carbon is that this carbon here is alpha to a carbonyl, and it is chiral, and it has a hydrogen, which means this can undergo the process of keto-enol tautomerization. And here's our enol form. Now, you may be wondering why this hydrogen and not one of these three. And that's because this is going to give us the more substituted alkene. So this is the more likely enol to form because it is more stable. It's going to be more energetically favored. So this is the enol that will form. Now, the thing that's interesting about this is that we're taking something that is sp3 hybridized, and it is chiral, and it is tetrahedral. So it has a 3D shape. When we turn it into the enol form, it becomes sp2 hybridized, which means it is now trigonal planar. It is flat. So when this hydrogen comes back to protonate at the alpha carbon, that hydrogen could end up coming from either direction. And if it comes from the opposite side, you're going to end up with the keto form, but the enantiomer of our original keto form. So if you start off with something that is pure, a single enantiomer of a compound, and it's put into aqueous acid, then this process of racemization will occur, and you will eventually end up with a 50-50 mixture. Imagine it like you have a jar of pennies, and you lay them out on a table all heads up, and you go through and systematically do heads or tails on every single one. You do a little coin flip. By the end, you may have a 50-50 mix. You may still have more heads than tails, but the more you do it, the closer you're going to get to that 50-50 mixture. And that's what's going to happen here. We have millions, billions, trillions of molecules, depending on how big your sample is. And if they are constantly undergoing this process of racemization, they are not going to come out the same every single time, and you will eventually end up with a 50-50 mixture. So what may have started off as a pure sample of the R enantiomer, like this one, every time it goes through the process of tautomerization and then to the enol form and then back to the keto form, it could come out the S form or the R form until you end up with that 50-50 mixture. Now, this is really more of a concept than it is a reaction. This is not a reaction I can test you over exactly. But when we talked back in chapter 6 about how there are some drugs that we are given as pure enantiomers, such as naproxen sodium, because one version of naproxen is helpful and the other one happens to be a toxin to our liver, there are other drugs that we are given as a racemic mixture, such as ibuprofen. And the reason ibuprofen is given to us as a racemic mixture is that it undergoes this process. It has a chiral alpha carbon that happens to have a hydrogen on it. And so when it goes into our body, which is aqueous and acidic, it goes through this process and it would turn into a 50-50 racemic mixture anyway. So there's no point in us taking an enantiomerically pure drug that our body is going to racemize anyway. And with ibuprofen, the two different versions, one helps us, the other one just doesn't do anything. It doesn't hurt us. So it's not dangerous to take the 50-50 racemic mixture. Now, another interesting thing that can happen through this process of tautomerization is that when you form the enol, it is possible that the enol reacts with a halogen, and you're able to put a single halogen atom on the alpha carbon. So remember again, the alpha carbon is the carbon that is directly attached to the carbonyl carbon. And in this case, we put a benzene ring on the other side so that there would not be any hydrogens on the other side of the carbonyl, so that we can focus on one particular alpha carbon. And this is only going to put one halogen on that carbon. The identity of the acid may change. You may see just H+, but you do have to have typically some sort of acid catalyst so that you can undergo this process of forming the enol. And then you end up attacking the bromine. I'm not going to have you go through the mechanism for this. This is one that you are welcome to memorize. Now, what's cool about this and useful is that if you create this or something like it, you are creating a primary alkyl halide. Is it a kind of congested primary alkyl halide? Sure, but it's still a primary alkyl halide. And if you combine it with a nice small nucleophile, such as maybe cyanide or maybe a sulfur with a methyl group, then that primary alkyl halide can undergo a nucleophilic addition. And that gives you the opportunity to do some pretty cool stuff at the alpha carbon and put new functional groups very near to a carbonyl, which could allow you to synthesize larger and more interesting, more important molecules. But this is ultimately why this chemistry is important and useful. But this is the reaction that we're talking about when we're talking about alpha halogenation right here. This is just a bonus.